Hello, I am Robin Hake and I'm currently doing my PhD at the University of Oldenburg at the Music Processing and Perception Lab led by Dr. Kai Siedenburg. And today I'm going to present you the research that we are currently working on. It's on the development of an adaptive test for musical scene analysis ability. I will quickly introduce you with the main concepts that we used here, namely the concepts of auditory scene analysis in the context of music, before we move on with the procedure and the results of the experiment. Auditory scene analysis is something that every one of us is experiencing on a daily basis, while having a chat at a cocktail party or while listening to music. In both cases, it's pretty likely that you face a central problem, dealing with mixtures of sounds. So instead of processing only a single acoustic signal, the auditory system needs to deal with multiple acoustic agents, which all overlap in time and frequency. Since different acoustic sources are active at the same time, only the sum of individual sound spectra will reach the listener's ear. And for that reason, the subsets of incoming auditory information must be grouped and separated in order to get correctly identified. This particular process has been named auditory scene analysis. And to say it in Albert Bregman's words, who coined the term of auditory scene analysis, auditory scene analysis is the process by which the auditory system separates the individual sounds in natural world situations. Most of the time, when auditory scene analysis is studied experimentally, the focus is on the subject area of speech and noise. However, we are more concerned with music. And to put it in Daniel Presnitzer's words, music arguably provides some of the most complex acoustic scenes that a human listener will ever encounter. In music, a relevant auditory scene analysis task would be to track a single instrument, like a violin, in the midst of a large ensemble. What you can see here is the actual spectrogram of an instrument, a bass, playing. Let's listen to this example. Things, however, become more complicated when more instruments join into the mixture. Let's listen to a composite of these instruments. Have you been able to hear out the bass? As many of you probably know, the spectrogram can map a sound as a frequency time function. And here you have a visual illustration of the difficult task that the auditory system must accomplish when not one, but multiple sources play at the same time. They overlap in time and frequency. Previous studies have investigated several underlying cues of the auditory scene analysis mechanisms. In vision, these descriptions would include objects' shape, size, distance, coloring, and so on. But in acoustics, these cues would be proximity and pitch and tempo, harmonicity, spatial location, temporal similarity, and so on. But nonetheless, there's plenty that we don't yet understand. In many studies, for example, researchers have reported substantial individual differences in performance even among seemingly homogeneous participants. And by looking from a perceptual perspective, many of these concepts have not been investigated in an ecologically valid realistic music scenario. Exactly for that reason, our objective was to develop an adaptive and ecologically valid computer-driven measurement instrument which is suitable for measuring musical auditory scene analysis ability of individuals with a wide range of abilities. Or to be more specific, we want to be able to measure auditory scene analysis performance of young, well-trained normal hearing participants as well as older hearing impaired individuals. So what did we do? In order to accomplish this objective, we make use of the open source Music Medley database, which includes recorded real-world multi-track music excerpts representing popular music genres like classical, rock, jazz, pop, and so on, of which we extracted 160 2-second long excerpts from 98 different songs. Each excerpt had a specific number of instruments playing, in this case 3. And 1 was chosen as a target instrument, here the lead voice. After a 1-second pause, a composite of all 3 instruments were playing. So what we did is that we opted for a two-alternative forced choice task that required participants to decide whether the single instrument, the lead voice, was part of the mixture of instruments. So let's listen to this example. We also increase the number of instruments playing in the mixture. In this example, a piano is a target instrument, followed again by a 1-second pause and the multiple instruments at the same time. Let's listen to this example. Our hypothesis is that by increasing the musical complexity in the scene, the task would become more difficult for participants. Within half of the trials, the target instrument was presented not in the mixture. And to ensure the same musical complexity, we choose excerpts in which a seventh instrument could replace the target instrument. So in case the piano was not played in the mixture, for example, the backing vocals would join in to fill the gap. In order to be able to tailor the test level of difficulty to the participants with different abilities, the excerpts varied in terms of the choice of the target instrument, which was varied between the lead voice, bass, piano, and guitar. In terms of the musical complexity, which is the number of instruments in the mixture, which we varied between 3 and 6 instruments. And on top of that, we employed a third parameter, the level ratio between the target and the mixture, which had 4 levels varying between 0 and -15 decibel, which should make the detection task more difficult. Let's listen to an example with the level ratio of -15.
That dog you love so much. That dog you love.
Let's move on to the procedure. Each participant had to complete all trials in which the target to mixture level ratio was presented randomly across trials. The experiment was conducted online, and all participants had to pass a headphone check, the Huggins pitch test. A questionnaire included the usual demographics, and we also added 2 subscales of the Goldsmith Musical Sophistication Index for musical training and musical perceptions. Now let's finally hop into the preliminary results. It should be noted here that this research is still ongoing and we are still recruiting more participants for this particular experiment. So far, 90 subjects participated in the study, of which 5 we had to exclude since the performance was on chance level. Of the remaining, 75 people had normal hearing, while 10 were hearing impaired. The mean age was 27 years, with a range of 18 to 69 years old. Let's have a look into the results. Here you can see the results of the first parameter, the choice of the target instrument. The box plots provided here are displayed as a percentage of correct answers averaged across participants and target instruments. The chance level is at 0.5 and the black dots represent averaged individual responses. Here we can see different response patterns for different target instruments. Lead voice was detected in the mix most often correctly, followed by piano and guitar, while bass seems to be a little bit special in this regard, as it is showing the highest variability, while also being perceived most difficultly within the mixture. This effect has been shown to be significant and having a relatively high effect size. Here you can see a similar plot showing box plots of responses splitted for musical complexity. Overall, it's more difficult to track a target in a more complex musical scene with 6 instruments compared with 3 instruments. This effect is also significant and has a considerable effect size. Let's move on to the third parameter, the level ratio between the target and the mixture. Within this figure, all 4 levels of the parameter is presented. Minus infinity, as is seen on the box plot on the left, represents all responses from items where the target instruments was not presented in the mixture. This figure illustrates that tracking the target instruments within the mixture becomes increasingly difficult with increasing level ratio, as it is seen in the nice linear trend of participants' responses for the respective conditions. This effect is the most robust one and shows by far the highest effect size. Now I'm going to present you some correlations. Displayed is the scatter plot of the subscale for musical perception of the Goldsmith Musical Sophistication Index as a function of the percentage of correctly identified items. The perception subscale has 9 items and participants have to give answers to questions like I can tell when people sing or play out of time or with the beat, or I am able to spot mistakes in a performance of a song even if I don't know the tune. We found a statistically significant trend in which individuals with high self-stated musical perception indeed identified more items correctly compared to individuals with low scores. A similar trend is observable for the subscale of the Musical Sophistication Index for musical training, which includes questions like I would consider myself as a musician, or I engage in a regular daily practice of a musical instruments for a specific amount of years. Actually, we found no relationship between performance and age whatsoever. However, as you can see here, this analysis is greatly underpowered as we have only a few participants above 30. Finally, let's talk about the implication of our work. The preliminary results indicate that all 3 parameters that we used are suitable factors to discriminate between listeners' abilities. And this indicates an excellent discrimination capability of all parameters of interest. However, we need to test a few more hearing impaired participants to be sure that our items are sufficient for all ranges of abilities. Despite that, we plan to run the experiment with the short 25 item long version among a very large sample. Furthermore, the established musical scene analysis tasks have to be validated under laboratory conditions. With the help of the advancements of the item response theory, this test will provide an efficient tool for evaluating musical auditory scene analysis performance of individuals with a wide range of abilities. To understand precisely what traits are being measured by this test, it is also useful to investigate how test scores correlate with other pre-established trait measures, like tests for mistuning perception, melody discrimination, or pitch discrimination. And altogether, this will give us the possibility to efficiently map out individual differences in a variety of music perception tasks across a diverse sample of participants. This is the end of my presentation. Thank you all for your attention. It has been a pleasure to present you our research, and I'm thrilled for all of your questions.